At the turn of the 20th century, we really thought we had the universe all figured out. It seemed like the big laws were all written, the fundamentals were understood, but two brand new, radical ideas, one about the immensely large and one about the impossibly small, were about to come along and shatter everything we thought we knew. So let's dive into the story of these two incredible revolutions.
Yeah, this quote from Nobel laureate Albert Michelson, it just perfectly sums up the vibe back then. The great work, it seemed, was done. Physicists were confident, just maybe a little too confident, that all they had left to do was kind of tidy up the final tiny details.
I mean, you had Newton's laws of motion, Maxwell's laws for electromagnetism. It all seemed to describe the entire universe with this beautiful clockwork precision. But there are a couple of stubborn little experimental results that just refused to fit the picture. And these weren't just loose ends, no. These were the first signs that a huge crack was about to open up in the very heart of physics.
Alright, so the first revolution kicks off with a pretty simple question about light that had a totally mind-bending answer. Specifically, it was about how fast light moves. And as you're going to see, that one little puzzle would completely flip our understanding of space, time, and gravity on its head.
Okay, to really get what's going on here, we have to talk about this one key idea, an inertial frame of reference. Basically, in classical physics, all steady motion is relative. So if you're on a perfectly smooth train, you honestly can't tell if you're moving or if the world is moving past you. There's no such thing as absolute motion. All of those inertial frames are equally valid. So here's the problem that broke everything. Common sense, your gut, tells you that if you're on a super fast spacecraft and you flick on a searchlight, someone watching you from the ground should see that light moving at the light speed plus your spaceship's speed. Makes perfect sense, right? But then experiments showed something that seemed totally impossible. No matter how fast you're moving, light always travels away from you at the exact same speed, about 300 million meters per second. This single stubborn fact just shattered classical physics.
So in 1905, this young patent clerk, Albert Einstein, came along and proposed this incredibly bold solution. He basically said, hey, what if this isn't a problem? What if this is just how the universe works? He built his whole theory on two simple but radical ideas. First, the laws of physics are the same for everyone in steady motion. And second, the speed of light is constant for everyone. Period. Full stop.
So if the speed of light is the cosmic speed limit, the one thing that refuses to change for anyone, then, something else has to give. And the most shocking consequence of all, it was time. Time itself isn't absolute. The faster you move through space, the slower you move through time, at least compared to someone standing still. This is where we get the famous twin paradox. So picture this. You've got twins. One twin, Dick, zooms off on a high-speed space trip while his sister Jane stays home on Earth. When he gets back, he will actually be younger than she is. For his 30-year trip, a full 50 years will have passed for Jane. And because Dick is the one who had to accelerate, turn around, and come back, he changed his frame of reference, he's the one who really experiences this time dilation. Now look, this isn't just some sci-fi thought experiment. This is a real, proven feature of our universe.
But Einstein wasn't done yet. Not even close. 10 years later, he came back and took on gravity. He realized that mass and energy don't create some kind of mysterious force that pulls things across empty space. Nope. Instead, they actually bend and warp the very fabric of reality, this four-dimensional thing we call space-time.
This is the classic way to picture it, and it's a great one. You imagine space-time is like a big, stretched-out rubber sheet. If you put a heavy bowling ball in the middle, it's going to create a deep curve. Now, if you roll a marble nearby, it's not being pulled by the ball, it's just following the curve in the sheet that the ball made. The physicist John Wheeler put it beautifully. Space-time tells matter how to move, matter tells space-time how to curve. That, right there, is gravity.
Okay, see, while all this relativity stuff is blowing people's minds, at the exact same time, there was another revolution happening. And honestly, it was even weirder. This time, it was all about the teeny tiny building blocks of matter itself.
So here was the big problem. Right, so we knew atoms had this positive center, the nucleus, and these negative electrons whizzing around it. But according to all the physics we knew, an orbiting electron should be constantly radiating away its energy, which means it should spiral into the nucleus in like a fraction of a second. Every atom in the universe should instantly collapse, but they don't. So why?
The guy who cracked this was Max Planck, and he came up with an idea that, at the time, sounded completely nuts. He said, look, Energy isn't this smooth, continuous thing, like water flowing from a faucet. Instead, it only comes in tiny, individual packets he called quanta. You can have one packet, or two, or three, but you can't have like 1.5. There's nothing in between.
And that one idea, the quanta, just blew the doors wide open to this totally bizarre new reality. In this quantum world, particles, like electrons, can also act like waves. We can never know exactly where something is and where it's going at the same time. And instead of smooth changes, reality makes these sudden quantum leaps between energy levels. Yeah, the whole idea of a predictable clockwork universe? Gone, replaced by a world run on pure chance and probability.
So, with these new quantum rules, physicists could finally start smashing atoms apart to see what's inside. And what they found was a whole zoo of new fundamental particles.
And in this particle zoo, they figured out something amazing about what forces actually are. A force, like electromagnetism, isn't some invisible field. It's literally particles being thrown back and forth between other particles. These are the force carriers.
Okay, how in the world does that work? Well, picture two people standing on skateboards. If they start throwing a basketball back and forth at each other, every time one throws and the other catches, the recoil is going to push them apart. That's basically how exchanging a particle creates a repulsive force.
But what about attraction? How does throwing something make you come together? Well, instead of throwing it at each other, imagine they're snatching the ball from each other's hands. Every time one grabs it, it pulls them closer together. And just like that, you've explained two of the universe's fundamental forces with a game of catch. Incredible! Okay, so we've got our two shiny new theories of reality. We've got Einstein's general relativity for the huge world of stars and galaxies, and we've got quantum mechanics for the tiny world of atoms and particles. The only problem? They absolutely hate each other. They just do not work together.
You've got general relativity over here, describing this big, smooth, continuous, predictable universe. And then you've got quantum mechanics, describing a universe that's jumpy, chunky, and based on pure probability. They're like two totally different languages. And when you try to use them together, like to describe the inside of a black hole or the very first second of the Big Bang, the math it completely falls apart. Total nonsense.
This is it. This is the holy grail of modern physics, the ultimate quest, to find a single, beautiful theory of everything that can unite these two and finally write the ultimate laws of the universe. It was a dream that even Einstein couldn't crack. He spent the last part of his life searching for it, but he never found it.
So today, our best shot at this unified theory is something called string theory. And its central idea is, well, it's pretty wild. It says that if you could zoom in on any particle, an electron, a quark, whatever, way, way, way down, you'd find it's not a dot. It's a tiny, vibrating loop of pure energy, a string. And just like a violin string can play different notes, every different particle we see is just a different note, a different vibration on these fundamental strings.
Now, here's the catch. For the math to actually work out, string theory needs something that's almost impossible to wrap your head around. That our universe doesn't just have 4 dimensions, 3 of space, 1 of time, but 10. The other 6 dimensions, they're just curled up, super, super tiny, way too small for us to ever notice.
So think about this journey. We started in a universe we thought we had all figured out, and we've traveled through warped space-time, taken bizarre quantum leaps, and explored a whole zoo of particles, all to arrive at this one final, mind-bending question. Could it be that all of reality, from the smallest quark to the largest galaxy cluster, is really just a giant cosmic symphony played on these unimaginably tiny, vibrating strings? Finding the answer to that, well, that's the future of physics.